Probably either they're not recorded or
They recorded. With no update like from the last month, I think so.
okay. I'll check. So our second midterm test is going to be on 14th of December at 5:40. What's that? So 14th is Friday. Yeah. 1-4. What's that?
Just 30 minutes more.
No, he's asking the term project. It's due 15th.
Because we have also a few days we will do.
Okay, so then project to 17th. 2 days? Because then I'm going to ask you to present your papers. So I need enough time for you to present them. Okay. Again, we'll make the midterm open book and open everything. No discussions.
Only 2 hours. Can we spend a little time for that?
Well, I'll make the questions shorter.
Yeah.
Okay. So, yeah, I think this time it's going to be more conceptual rather than, it's not going to be too calculationally heavy. So, again, same rules. We'll talk about it. Do you have any questions before we begin?
Our presentation for the project.
Mm-hmm. Is that what I wrote in the email? Okay. So let me check the calendar. Classes end on 30th or 31st. Then we'll use that week. Or, we will see. So you will still have 1 week to be prepared. We have 9 people in total. And if we say like 15 minutes each, then it will be like 135 minutes, which is slightly more than 2 hours. So we'll have enough time. We can do both Tuesday and Friday. So we'll have enough time to do all the presentations. And the format of the presentation is up to you. You can prepare a PowerPoint slide, or you can write it over lecture notes, some sort of notes that you prepare, and use the whiteboard. I'm going to leave it up to you. But it should be as informative as possible. So I don't expect you to go too much in depth in the presentation, but try to be as informative as possible. Make sure that we learn new things that we haven't learned in this class, or but it, of course, is going to be related to this class, but we haven't seen in too much detail in this class. Okay. Right, so last time we finished talking about quantum wires. So we start our journey from 3D to 2D to 1D, and the next is 0D. And when we talk about zero-dimensional objects, we talk about quantum dots. And related to quantum dots, we'll talk about single electron tunneling. Okay? So, it's a quantum dot. Well, we follow our definition that we did for 2D and 1D confinement. The idea is that we have, I don't know, some sort of, indeed, still a three-dimensional object. Let's say it has, it's a cubic object with sides of length L, and this size is comparable to the Fermi wavelength of the electrons inside. So this is my Fermi wavelength. Okay? So with that definition, we also calculated the density of states for zero-dimensional object, and it was 2 over volume of this thing, and e.g. So this is called the Dirac delta function. So if you look at the spectrum, this is what we'll see. So these are the energy values. So at certain energies, we have such spikes for density of states. Okay, so this is you can think this function as an infinitely narrow Gaussian. Okay, so it just gives very well-defined discrete energy states for each value. So EG is, no, it's not the gap, it's the energy corresponding to each energy state. Okay. Each state in the quantum dot. So in a way, if you look at the these discrete energy levels, we can resemble this thing to artificial atoms. And indeed, we have seen a very similar energy spectrum in an infinite potential well. We studied it in 1 dimension and also in 3 dimensions. And we have seen these discrete energy levels for a 1-dimensional infinite potential well. So, in a way, quantum dot is an object that we can sort of model with an infinite potential well. Okay? So, one thing interesting about these artificial atoms is that we can really mimic atoms with the quantum dots. So when we consider the size of an atom, we are roughly talking about a 0.1 nanometer sized object. And quantum dots are typically 10 to 100 nanometers in size. So when we consider the energies, there is a 1 over L squared type of relation. So here we are looking at energies on the order of about an electron volt. But in this case, we will be talking about energies on the order of 0.1 milli-electron volt. So we have roughly 10 to the 4 times change in the energy scale. And the good thing about this change is that we can tune the energy separation by changing the size or certain properties of our quantum dot. And also we can play with certain properties of this atom in under various conditions. What's that? Millielectron volt. Okay, so there's this millielectron volt. So there's like roughly 10 to 4 orders of magnitude reduction in the energy scale. Okay, and indeed this creation of artificial atoms allow people to do interesting quantum experiments on these artificial atoms. Like they tested the limits of the Hund's rule, the ordering of the electronic configuration, and so on. We'll try to see some of them. So there are several types of quantum dots. We can say we have semiconducting quantum dots. So
which methods you told that they use for the creation of the artificial atoms? One you told that it is a ordering of electronic configuration for the creation of artificial.
no, I haven't told. Like when you make a zero-dimensional object, it's like an artificial atom. That's what I told. I haven't mentioned anything about how you make artificial atoms. Okay? So this thing just resembles an artificial atom because it has discrete, well-defined energy state.
About the creation of artificial atoms.
Did I?
You said creation.
Did I say it? What did I say? I completely forgot. Sorry.
You said creation of artificial experiments. They do some quantum experiments.
Yes. So they make experiments that you cannot make on regular atoms because of this energy scale. So for instance, if you want to see the effect of magnetic field on the ordering of the energy levels, you need something like 10 to the 4 Tesla magnetic field so that you can start playing with the Hund's rule, which is non-existent. You cannot create 10 to the 4 Tesla in the lab environment. The maximum we can go is like few hundred Tesla, and that's very exceptional. I think the world record is something like 150 Tesla or so. So by changing this energy scale, you change the requirement for the magnetic field so that you can play with the ordering of the orbitals, if you like. So things like that, okay? Now, one way to create quantum dots is having semiconducting quantum or nanoparticles. You can find lots of different semiconducting quantum particles. Typically, cadmium chalcogens, where this is selenium, sulfur, or tellurium. You find it in such forms, or there are lead chalcogens. Again, sulfur, selenium, and tellurium is used, and there are many examples of that sort. And typical sizes are I don't know, it really depends, but you can go from a few nanometers to tens of nanometers while still maintaining the quantum effects. And these are commercially available, and these are also used in applications. You can go and buy a quantum dot TV from Samsung if you like. The way it works is that they have the LCD panel in the front, and then for the backlight you need to do some sort of light conversion to create the lifelike real colors. So what they do is they have this array of quantum dots on the back, and then they illuminate this quantum dot with a UV light So what happens is that quantum absorbs the UV and then it emits in very specific like frequency range. So there are 3 or more types of quantum dots, sizes of quantum dots. So you excite them with a UV and then they down convert this light to the various wavelengths. So you cover a broad range of the spectrum to create better colors. So you can find applications of such semiconducting quantum dots even today. But yeah.
It's not just for commercial, it's really using this technology.
So
When I heard it, I take it as just a similar LCD and they're just marketing.
no, that's what I'm saying. Commercial means you can go and buy commercial products. Okay? So it's not just for experimental purposes. It's really something that you can buy in a product. And what else? I'm not sure if it is an application, but there are demonstrations of things like they attach certain molecules, probably not the lead one, but some other cadmium, lead. They're all toxic to a certain extent. But on certain quantum dots, they add some ligands that are very specific to certain proteins, and they inject these quantum dots to typically, I've seen this study on mice. So they inject this into bloodstream of mice, and then this specific protein only attaches to certain type of cancer. So in the end, after they wait long enough, so this is a mice, okay. So, what's that? Oh, use your imagination. Okay, so, whiskers. Do mice have whiskers? No, that's turning into cat. Okay, whatever. Some sort of animal. Okay, and that quantum dot accumulates on that specific cancer region, and then they image this region with a certain imaging technique, and they find where the cancer cell or cancer is, and so on. So there are some applications in ranging from biology to chemistry to physics, and again, you can. These are commercially accessible stuff. Then there are metallic types. But I don't want to say quantum dots to metallic nanoparticles. Because the difficulty is basically similar to quantum wires. The size requirement, length, is so small that typically you need only a few nanometers in size, in diameter, so that you can really start calling these particles as quantum dots. So most of the metallic nanoparticles cannot be treated as quantum dots because of this extremely short Fermi wavelength. So most of them, I guess, they display these interesting properties because of not their quantum properties, but their different interactions with the environment. But in both cases, both isolated semiconducting and isolated metallic quantum dots, you need these ligands that are attached to the quantum dot, okay, so that they can stay stable. If you remove these ligands, they get oxidized, they lose their structure, and so on. So typically these, when you consider isolated quantum dots, you have to consider them with the ligands that are surrounding them. Our focus is going to be on quantum dots that are created on 2D electron gas. So how can you create a quantum dot in a 2D electron gas? So again, this is our gallium arsenide, gallium arsenide doped with aluminum, and then we have this 2D electron gas that is embedded in between the interface. So it's 2DEC, 2D electron gas. Okay, 2D electron gas. And this is gallium aluminum arsenide substrate. So we would like to have a more controllable environment so that we can really study the mesoscopic effects in these quantum dots. The difficulty with these guys, they're surrounded by ligands, and making contacts with these free quantum dots is rather difficult. So that's what we do. So the idea here is this. Let me look at the surface from the top. Now you have this 2D electron gas that's underneath the surface layer. So what you do is you put some metallic regions. I'll explain why we have this very specific configuration. Okay, so you deposit these gate electrodes. They don't have direct connection with the 2D electron gas. So this one is called the finger gate. This one is called the center gate. And typically this one is called Q1 gate, and this is Q2 gate. So we have 4 gates that we can apply potential to. And the idea, I mean, if you look at the dimensions of this object, typically what we are looking at here is about a micron or so. So the 2D electron gas has this very high mobility, and also it has very long Fermi wavelengths. So you can make, it doesn't have to be in the nano range, you can make it in the micro range and still observe the quantum effects. Okay, so the idea here is that you have this 2D electron gas, and by applying appropriate voltages to these gates, you want to deplete the electron gas here around the gates, but only leave a collection of electrons at the center. And this collection of electrons will, because of this confinement in 3 dimensions, will start acting as a quantum. Is it clear? So, yeah, sure. So we have this 2D electron gas, okay, that's in between these layers. So the idea is to isolate a collection of electrons from the rest of the electrons in a narrow region of space. The way to do it is you put these gates. They don't have direct contact with the 2D electron gas there. They have insulating layers underneath. So when you apply potential to these gates, I mean, we could just do it as 2 gates, but then so, or even we could do a ring like this, but then this would be a ring like this, so you have this metallic gate here. Okay, so when you apply a certain bias to these gates, it could be a negative bias, okay, so some negative voltage, then the net effect is that you repel some of the electrons outside, but inside you confine a certain number of electrons depending on the gate voltage that you apply. Okay, and so you deplete these regions here or under this gate region. So the collection of electrons that you have in the center or here will now feel the confinement in 2D. Okay, so you already have 2D electron gas that's confined in one dimension. And with the gates, you bring extra two dimensions of confinement. So you end up with an object that's confined in 3 dimensions. So you end up with a 0-dimensional quantum dot. Is it clear?
You meant that like with the digitalization of
Mhm.
electrons which was inside that
Yes.
region that will make the quantum dot.
Well, they will behave as quantum objects.
But I don't understand what property like convincing them could be made by the quantum dot.
Because they're confined in 3 dimensions. Okay, so there's already confinement in 1 dimension. That's why we call this 2D electron gas. And then with the gate, you confine in 2 other dimensions. So you confine them in 3 dimensions.
Okay, 2D from this picture and 1D from the base.
Well, no, 1D from here, 2D from the gate. This is 2D electron gas. Now we have a confined electron and we can start playing with it. The reason why we have these individual gates is that we can controllably couple this quantum dot to the external to the electron gas. So the idea is by tuning the gate voltages, I'd like to have some electrons to jump in and some electrons to jump out of this quantum dot. Okay. Now, let me draw what happens when I apply bias to the gates in a controlled way. So the overall device structure actually has 2 more electrodes that are in connection with the electron gas. We can name them source and drain. So this is where we take the measurements from. But now I'm going to draw this. So this experiment performed at 25 millikelvin. So I'll write down the conditions to form this 2D electron gas and really observe its quantum properties as well. But let me show you. So this is 0, this is minus 0.2, this is minus 0.4, this is minus 0.6, minus 0.8. Okay, this is the gate voltage. And this is conductance in units of E square over H. And what we have is phi and 15. So what happens is when you apply gate bias between the finger gate and the center gate. So this gate bias corresponds to the finger and the center gate. What you get is some decrease in conductance, and it stays that way. So it never hits 0. Then we have 2 other ways to control. So what happens is that it goes down, and then it does these steps, and it's 0 here. Let's say this is between 2,2 and the finger gate. And finally, there's also it's very similar. This one is what this graph telling us is when you change the bias between Q1 and the finger gate, so let's say you ground one of them, okay, so you ground the finger gate and apply some negative bias to Q1, then the conductance gradually decreases, and then it performs these conductance steps that we have seen in quantum point contacts. Okay, so these are conductance steps we observe in quantum point contacts. So you are basically pinching off this contact, and at some point now the electron that tries to go in and out of this region starts assuming this quantized conductance. So we observe these steps. And at certain gate bias, so once this is at a certain value, we completely pinch off the quantum dot. Okay. So no electron now can enter into this region. Conductance goes down to zero. There's not, besides these conductance steps, there's not much interesting going on. Actually, this is somewhat something we expected because if you think about it, if you apply a large enough gate bias, you deplete all the electrons here, so there's no available energy states left for electrons to go through. The conductance diminishes. Now, my drawing is rather poor, but there's one more plateau here that's left behind, okay, where the conductance is exactly 2e squared over h. And at this point, we call this point as the working point for the quantum number. So if I tune both of the gate voltages to this value, okay, both of the gate biases to this value, then this will be my working point because there's exactly a certain amount of electrons left behind in this region that interacts barely with the surrounding environment. Okay. So that's why we name this point as the working point. What's that? Well, as we'll see, we must treat these electrons as interacting electrons. Otherwise, we cannot explain most of the features that we observe. That's actually going to be the main difference between our single electron treatment of electrons in an infinite potential realm and a real quantum realm. Because now we are talking about only a few electrons within this object. And if we ignore the interactions between the electrons, then this means we cannot explain pretty much any of the things that we observe in quantum dots. So we're going to start factoring the electron-electron interactions into account. So now at this working point, this part, I'm going to draw two more graphs. I'm going to draw a graph like this. Okay, so now in the first case, I'll draw these gates as such. What I do is this. All of these gates are grounded, okay, so they're connected to ground, and I tune the bias on the finger gate. And in the second case, all of these are grounded, and I tune the bias on this gate. Okay, and again measure the conductance of the quantum dot. So I have again conductance in the units of E squared over H. So this is 0, this is 0.5, this is 1, this is 1.5. Again, I have 0, 0.1, 0.2, 0.3, 0.4, and so on. And again, the experiments are performed under 20 millikelvin. Okay. Yes. That one was 25 millikelvin, this is 20 millikelvin. Well, no, that's not what I'm going to talk about. But I don't think 5 millikelvin affects that much. I mean, I haven't cited the paper that I took this from, but that's at that's the temperature where they do this experiment at. So, and the gate voltage is here minus 0.6, and it goes down to minus 0.8. So this is the gate bias in volts. Okay, and what we observe here is something like this. It goes down, goes up again, and then we start observing these very fine oscillations. Okay, and then it goes down to 0. And then in this case, it starts oscillating again, and then it hits 0. So what happens here is that the conductance, so conductance of the quantum dot, so electrons going from source to drain, doesn't follow some sort of monotonic change, but rather there are two types of oscillations. One happens on a slower response, if you like. The other happens on a much faster change with the gate bias. So there are two effects that we are going to discuss that result in such oscillations. One of them is called the Coulomb blockade. And the other one is due to quantization of the kinetic energy of the electrons. So basically quantization of the energies within the quantum dot. So as a result, what we see is resonances in transmission, and we'll try to explain why such resonances happen for the electrons' motion that are entering into a quantum dot and leaving from the quantum dot. Okay, so sure.
So this diagrams that we have here, they represent the electrons that they go from the source and drain to
Yes, through the quantum dot.
through the quantum.
Yeah.
At that one, we calculated
This is the exact same thing. I just try to draw So what I tune here, so it's the exact same diagram, I just tried to make a schematic of that. I ground these three contacts, these three gates, I'm sorry, and then I tune the gate bias on the finger gate. So its net effect is basically pinching off both contacts at the same time or opening them both at the same time. In this case, what we see is this is open because they're grounded, so my 2D electron gas can reach in here, but I have a single junction here. Okay, so in a way, that's the fundamental difference between these two.
Does that mean that the sort of potential that is applied on quantum part is different for the electrons that it passing by? That's the thing we are doing here, or?
Both yes and no. Yes, because now, as we'll see, the way we change, I mean, perhaps I should write down the equations, but the way you should be treating this now, you cannot treat the energy levels as isolated energies, and you cannot treat the case where you have n electrons and n plus 1 electrons as the same. What happens is, you're right, depending on the voltage that I apply to the gate, now I either allow 1 electron to enter in or I don't allow. So it's yes, you modify the potential inside indirectly by allowing or not allowing electrons to go in. But I don't think we have, by just changing the gate bias, you tune the energy levels too much. Okay? Because effectively what you're doing is the electrons, as you apply bias to here, you create a depletion region around the gate, which effectively screens the bias that you apply from these electrons. So there's screening going on actually. But indirectly, by changing the bias, yes, you affect the energy levels of the system. Okay? So now, how do we explain these oscillations? So how do we treat quantum dots? Now, the simplest thing is we know that the density of states for a 2D electron gas was given by this constant value. Okay, and now I take spin degeneracy into account. So I have spin up and spin down electrons. And once you confine this 2D electron gas, you'll see that the energy separation between the energy levels is going to be something roughly MA. And this is the answer actually that we know from before in the infinite potential well. That's sort of what we had for the energy separations, pi h bar squared divided by the size of the quantum well. But as I mentioned, this description is not adequate to explain what's going on, because now we have to take interactions into account. Now, let me try to schematically explain what's going on inside a quantum dot when we try to put an electron in or take an electron out of the quantum dot. So I guess it will become more clear what I mean. Let me keep that diagram. It's very complicated, but still may benefit from it. Now, what I have is something like this schematically. Okay, so this is some sort of, I define my zero as such, and then my Fermi level. So this is no bias case, and what we are looking at here is these regions are the depleted regions, so these are the junctions. So basically, these are junctions, and for apparent reasons we call them tunneling junctions, because indeed under right conditions, under working conditions, you isolate your quantum dot from the rest of the 2D electron gas, so you create a region with no electrons, so it forms a potential barrier. So the only way for your electrons to go from this side into the quantum dot, or from quantum dot to the outside, is via tunneling. So these are tunneling junctions. Okay? And within the quantum dot, that's what we have. We have discrete energy levels. Okay? And these energy levels are filled with spin up and spin down electrons. Okay? And then there are more energy levels that goes all the way up. So this is the case where we haven't applied any bias or anything. Okay, so what happens when I put one electron into this system? Well, so the energy, now first perhaps I should draw some sort of equivalent circuit for this guy so that I can define the energy in an easier way. So if you consider this quantum dot, that's sort of what I am looking at. I have two capacitors. Let's call this source drain, and this is my first quantum dot. So the capacitance S1 and D1 sort of models my system. So in order to, but these are not regular capacitors of course, but in order to put one charge into this capacitor through here into this quantum dot, then I have to give this much energy into my system. So when a capacitor is charged, in other words, it will gain this much energy because of this charging. Now when I charge up this quantum dot, the effect is going to be something like this. So we'll discuss the details of why this happens so. But let me draw schematically first. So now, again, I have my energy levels. Okay. And I have these electrons, but now I put one more electron into the system. Okay, still this is my Fermi level, and this Fermi level here is lower than the Fermi level here because of the bias that I applied. But now from this base level, the energy of that potential well has increased by E squared over 2C. Okay, because of the electron that I put in. Okay, that's good. Now, but this electron has higher energy than the Fermi level there, so it can move through. So first, I have to apply enough bias to my source and drain so that I can put this electron in. As soon as I shifted the energy levels, but now I can transfer this electron or these as well to here. So if I plot, this can be source drain bias, or I can give the same effect by tuning the width of the gates. It really doesn't matter. So this is some sort of voltage, and this is the current that goes through source and drain. What I observe is bumps like this. And these bumps are with regular intervals that are determined by the energy spacing of my quantum dot. Okay? So this is resonant tunneling. Okay, so, and that's one of the reasons why we see such oscillations at regular intervals in our system. Let's give a 10-minute break, and then we'll go into more details of how to understand resonant tunneling, and also we'll talk about Coulomb blockade. What else would, yeah, that's the problem. So I think after every, I don't know, 10 growths or so, you should clean it. So I don't know, we need some sort of counter, or we need to keep track of that. No, no, you cannot check that. Don't, I mean, you can, but it's not going to help, because the vacuum line is completely different than where the blockage happens. No, there won't be any leakage. Don't worry about it, because we work at positive pressures, not negative pressures. So what you should really do is check that junction all the time. Okay. or narrow crystals?
Free crystal.
Interesting. Maybe we need to explore it. Okay, so let's start talking about Coulomb blockade in quantum dots. Now, as the name suggests, it's blocking off another electron coming into quantum dot by an electron that's already inside the quantum dot. So if you think about let me use the schematic here. So again, I have this depletion region or the tunneling junction, and I have an electron here, and I have a state that's available, but it has an energy higher than my Fermi level on the other side of the tunneling junction. And then I have a Fermi level here. Okay. Now, in this case, the charging energy, okay, is already so large that I cannot put this electron. This state is already filled, so I cannot put this electron in here simply because there's an electron in that position. So what I need to do is I need to lower down the Fermi energy here. So I need to apply a bias to this quantum dot between the source and drain. So the new configuration will roughly become something like this. So I have this filled state, and then the new Fermi level is equal to the energy level here. So under this condition, now this electron can move out, and this electron can move in, of course, to the lower state. Okay? So the energy required, or the bias that I have to apply, is equivalent to the charge divided by the capacitance that I define as C11, which is given by the capacitance CS1 plus CD1. Okay? So I need to apply at least this much of a potential difference so that I can put one electron in. But as soon as this electron jumps back in, that's what's going to happen. So, draw this again. Empty state now is still at that level. So as soon as I put this electron depleted here, and then I put another electron in because of the charging energy, now this is the new configuration that I'm going to have. So I cannot put any more electron into this system till this leaves the system. So if you think about it, now we defined some sort of course we defined some sort of time scale to the problem. So if you really want to observe Coulomb blockade, then there are two conditions that you have to satisfy. One of them is the energy of the so this is thermally activated electron transfer energy. It should be on the order of kBt. And then another thing is we need to define a time scale. Okay, so this is one of the conditions. And then the time scale that I'm going to define is basically given by e squared over 2c. It should be greater than h bar over tau. So it's the time the electron diffuses to the contact leads. Now, with these two conditions, I can define a resistance to my system. So tau should be roughly on the order of RC, resistance of the quantum dot, or I should say from source to drain, and the capacitance of the system. Okay, so this is the go back here. So when I combine these two equations, roughly this is what I'm going to end up with. R has to be much greater than h bar over e squared. And this is not a too much of a surprising result, because the resistance must be much more than the conductance quantum of resistance. And the temperatures we are looking at, so this is the resistance condition, and the temperatures we are looking at is really on the order of millikelvins, tens of millikelvins. So under these conditions, we can see Coulomb blockade oscillations, and otherwise the thermal smearing, so this energy difference between these two states, the charging of the states, if it is comparable to the thermal energy, then you'll not see the Coulomb blockade. And indeed, what you get is going to be something like this if I plot the source drain current. So this is the current, and you get something like that at 4.2 Kelvin. This is the voltage. Okay, so it starts from 0. I mean, numbers are really not important, but when you go down to 50 millikelvin, this is what you get. So this region, it really comes from so in a high temperature case, the thermal smearing of these states, now you have overlapping states because your electrons are thermally activated. So your quantum dot is like a conductive object. But when you lower the temperature to a level, excuse me, where you can really observe the energy of charging is much greater than the, not much greater, it's comparable to or greater than the thermal energy, then you start seeing that quantum dot, the energy transfer for the quantum dot happens at a certain threshold value. So sorry?
Can you repeat this concept again?
Sure. So, should I take it from the beginning or just that part? So the idea there is, perhaps I should give you more details about the figure. Let me see. So let me give you some numbers. Was it this one? see it in here, yes. So, now, this is sort of my system. In the most simplest case, I can model my system as such. So I have an ammeter, I apply a bias, and this is my tunneling junction. Okay? So what I'm after is measuring the current that goes through this tunneling junction based on the voltage that I apply. And at large enough temperatures, I don't see this Coulomb gap, I can name it as such, simply because at low temperatures, I have really discrete states. There's no thermal smearing, okay? My electrons basically assume they don't move around, they don't wiggle around, if you like. So they assume pretty much well-defined energy levels within the quantum dot. This results in that charging effect that I just tried to explain. So in order to send an electron in, you need to overcome this Coulomb repulsion between the electrons that's just outside of the quantum dot and just inside the quantum dot. So what you do is, until you reach a certain threshold value, starting from 0 millivolt bias to a certain number, you don't overcome that energy because it's something like E over the voltage, that the bias that you have to apply is something like E over capacitance of the whole thing. Okay, so it creates a zero response in your system. So you start tuning on the bias gradually, nothing, no current flows, because no electron can enter into the quantum dot, into the drain contact. Once you tune the bias, once you tilt the level to such an extent that now this energy level is aligned, or you lower this down enough so that an electron can jump to the drain, at that point, the conduction will begin. So you start repeating this cycle. Electron will jump here. Immediately, the levels will shift to this configuration now, but you still have an available state. Another electron will jump to this point. Again, we are back at this configuration, so it will start moving back and forth. But the net result is going to be basically at that temperature, as you increase the bias, you'll start seeing more and more levels will fall within here. So I only draw 2 levels, but as you increase the bias, more and more levels will come in. So it means you're going to be able to transfer more and more electrons, which means more current is going to pass through your device. But the difference, that this is from a real... Yes, so to be able to open up this Coulomb gap, and that's the condition you need. And this paper where they have shown this is Delsing PhysRev B 1990. Okay. So this is an experimental result. Now, another thing that I would like to mention is by the way, this Coulomb blockade is quite observable in many experiments, especially whenever you have a quantum point contact under correct conditions, you can observe Coulomb blockade oscillations. Because, for instance, I remember observing these Coulomb blockade oscillations in quantum dots. Sorry, not quantum dots, carbon nanotubes. And in our previous lecture, we talked about you can never really make a good contact to a quantum carbon nanotube. The reason is that you always have this tunneling barrier between carbon nanotube and the drain or source contacts, the metal contacts that you have. So with this tunneling junction, what happens is that you sort of replicate a similar scenario. So an electron enters in, it charges up the nanotube, and then the next electron either has to wait for that electron to leave the system, or you have to increase the energy of the bias. So even in carbon nanotubes at low temperatures, you can see these Coulomb blockade oscillations during the measurements. So, well, there's no advantage. So it's just a phenomenon. What's that? What's that?
It just
So,
gives you a movement of the single electron in the system.
well, it's really, I don't know. I mean, it's
It is also observed in the single electron transistor as well.
yes, it is also observed in single electron transistors, and that's that's what we are going to talk about. It.
Because I was studying that only single electron is observed in the experiment, but the idea behind this was that only one electron behaves at one time.
So, yes. So the idea is that it's really electrons can enter one by one into the system because of the large charging energy that's required. So, really, we are talking about the energy separation is something. I shouldn't say large, but it's at the level that under certain bias conditions, only a single electron can live within the quantum dot. And this will create a Coulomb repulsion. So it will locally increase the energy that's required to put one more electron into the system. So indeed, that's what you observe when you bias and try to send current through it. You really see discrete charges coming in and out of the quantum dot.
Every time we have to tune the bias voltages.
What's that?
Every time we have to tune the bias voltages.
To do what?
Like if the energy will be greater than this relation, KBT.
I didn't get the question.
For the shifting of the levels, you said that like if the distance between the levels should be lower, something.
Energy between the levels
Energy difference between the levels.
should be what?
Like I don't know how to explain.
I said the difference between the source and drain
Mm-hmm.
levels should be manipulated every time by chemical in order to constantly.
Yeah, of course, of course. So, but you don't have to play it back and forth. Like, this is a condition. Once you have this condition satisfied, then you will start have electrons passing through the device, one by one. But yes, they'll pass. So you'll have a finite current going through your system. Okay.
So this also can be thought as a relaxation time for the.
Exactly. So it's you can say it's a time for electrons to tunnel, which is not the best way of describing it, but yeah, it's some sort of relaxation time for electrons to come from this contact and end up in the other contact.
And one more, here you didn't, I think, include the spin algorithm, right?
Yes, we didn't include the spin.
This is the spin recipe.
Yes.
So if can we do this thing recreationally for spin up or down?
I think it really doesn't matter for this simple case that we discussed, because I've never seen any reference to spin in any of these studies. Then it matters. It matters a lot. And actually, I'm going to write down I will write down the equation, but it matters because when you apply magnetic field, then you have two net effects. You will get spin splitting because of the Zeeman effect. Also, now you're going to create Landau-like energy states. So that magnetic field will cause electrons to behave in a different way. So,
In quantum information, like, for
Mhm.
example, they care about,
Yes.
about these skills about
Mhm.
to save
Yeah.
information on that. Like in hanging two or three of
Mhm.
these beside each other, I think it's
well, no, it's, yeah, people do, but then this time scale issue comes into play. Still, even at 20 millikelvins, these electrons are not completely isolated from the environment. So the coherence is extremely, extremely big challenge in these planar quantum dots.
So it's not a good candidate.
I don't think they are good candidates because any disorder in this 2D electron gas, any disorder in the system will affect the entanglement of these quantum states. And again, no matter what you do, there is this tiny interaction between the environment and the quantum dot, the electrons within the well. So you always have dephasing. Yes, yes. So, I wasn't planning into going into details of that, but I don't think it's perhaps for the next lecture I should do some research on what people have done. To be honest, I don't know much details, but perhaps somehow they overcome these problems in more recent studies, because these books and everything that I prepared, this lecture notes, are from 90s, late 90s or early 2000s. They are not late 2010 or things like that. So maybe they have overcome these problems with better molecular beam epitaxy systems and so on, so they can fabricate much better structures, and they increase the dephasing time. Who knows? So this D-wave, the quantum computers, I think they use 2D electron gases, but then
They can use the same after it's not for this possible.
I'm not trying to remember the. But then they have only, I don't know, how many qubits? 16 in the most in the most recent one they have 16 qubits, and I don't know if you have seen that D-wave quantum computer, but it's like a room large stuff, and most of the thing is for the dilution fridge to make it that go down to 5 millikelvin. So I think the trick they use is they lower the temperature to an extent that they can have this 1 or 2 hours of coherence. So, yeah. Any other comments or questions? So, I mean, thanks for bringing that up, but you might be thinking that these are just for experimental curiosity, but there's actually more to it. Yes, the initial idea of studying these systems, perhaps to study quantum mechanical objects and how well quantum mechanics describes these systems, but now they're evolving into something much more bigger than what we discussed, and just to feed our curiosity. Quantum computation is one of them. Pretty much the only one that I know, actually. I mean, who knows? These are just now staying on the experimental tables and just few niche applications. But 10, 20 years from this time on, perhaps with better design of the 2D electron gas, better materials, perhaps with the 2D materials and heterostructures of these 2D materials, we'll be able to increase these temperatures to 4.2 Kelvin, And you can think that 4.2 Kelvin is like a low temperature, but it is not. For these purposes, 4.2 Kelvin is the easily accessible temperature that you can have, because to reach down to 4.2 Kelvin, you need to spend something like $30,000. To reach down to 50 millikelvin, you need to spend $200,000. So there's like 5-6 times difference between the money that you have to spend. And I'm talking about for 4.2 Kelvin setup, you can really have large areas. By large area, I mean this big areas. You can easily cool down with a $30,000 system. For 50 millikelvin system, it's typically a huge thing, huge object with lots of extra pieces of equipment, and the area that you can cool down is nothing bigger than this. So going from 50 millikelvin to 4.2 millikelvin with new materials may actually open up new dimensions in quantum computation and study of these systems. We should also be looking at these experiments in that regard as well. And also these are quite recent developments. I mean, 1990s, you rarely see things in lectures that are beyond 1950s, because these experiments really became available after making better and purer devices that has 2D electron gases. Okay. Now, the next thing that I would like to talk about is before, perhaps, let me see my notes. I really jump back and forth, but I'm going to talk about single electron tunneling. I'm going to leave the details to Ali, since it's his topic. Single electron tunneling. If you remember from our first few lectures, tunneling was something like this. We have, let's say this is some sort of energy, and then we have a potential barrier, okay, and then I have a quantum object that has some energy that's less than V0. And the idea was, the way we studied is that we have a plane wave that comes to this barrier, and then when we solve the Schrödinger equation, we realize that even for the barrier region, we have a solution that exponentially decays. So in a way, there is some probability of finding the particle within the barrier region, and then with a smaller amplitude, that wave has a probability of passing from this side to the other side. And the way we advertised this thing was, this is something that you cannot observe classically. It's like, it's not like that, but it's easier to visualize it that way. You throw a ball to a wall, and then it just appears on the other side. Of course, it's not the it's not even a good analogy, but in essence, that's what we see here. But in reality, what happens is that we are dealing with a wave, and this evanescent wave, if it couples to the other side, then it keeps traveling on. So this is like a near field effect in electronics or in electromagnetic waves. So if you get accustomed to work with waves, then this thing becomes extremely normal. But of course, in a physical object, that can, once it's on this side, and then the idea of it appearing on the other side with a certain probability is, of course, rather odd. But there are experiments where they showed tunneling of objects as large as buckyballs, carbon-60, the arrangement. Yeah, so it's real. It happens. Okay, so in the case of single electron tunneling, now this was more of the idea behind the tunneling, but if you consider an electron, that's what we said earlier. Actually, electron is more like a wave packet rather than a plane wave. Actually, you cannot define an electron with a plane wave. You have to use the superposition of these plane waves, add them up with different momenta, and then the electron is a wave packet. And then this wave packet travels in a medium, and then whenever it encounters such an obstacle that has that forms an energy barrier, then what happens is that now not the electron itself, but the probabilities. So a wave packet with certain probability will keep traveling that way, and some remaining package will bounce back and travel. And once you make the measurement with some probability, you'll find that your electron is traveling back, bounced off from this potential barrier. But with a finite probability, you'll see that it's traveling forward. Now, when we consider a quantum dot, now it's something like that. Let me draw the schematic. Again, I have a tunneling barrier, just like in that case, a region of space where the energy, so the Fermi energy now defines the energy of my electron, is lower than whatever energy is the top of the energy of that barrier. So in essence, I'm sending an electron to a barrier, and I expect it to go through or bounce back. And of course, there are many factors, like, for instance, in this case, we assume that here I have zero potential, but you can say, no, this is not zero potential. There is the landscape is something like this. Then an electron with energy of this level cannot tunnel simply because this will decay and die off. So there are other considerations. So really the Fermi level on the source side and the drain side affects, but if you have the same Fermi levels and nothing odd going on, then we are looking at the same picture over there. So let me see what I have. Now let's say I have a current I, okay, and charge on the junction is given by current times T, okay, and Q minus E squared divided by 2C. This is the energy of the junction with this Q in, should be less than E squared over 2C, so that the tunneling can be possible. Okay, and this simply says so the charge in the junction, on the junction, should be greater than E over 2. So after tunneling, if I assume that my Q is equal to E over 2, since I removed one charge, after tunneling, Q will become roughly equal to minus E over 2. And it takes E over I until Q becomes E over 2. So let me draw the schematic of the circuit. So I have a potential source here and a very large resistor. It really doesn't matter, but the resistance that I know of. And then I have my tunneling junction. And then an ammeter that I can read the current. Okay, so the setup that I have here is to basically measure the amount of Q that it takes to charge up this tunneling junction. So one experiment that you can perform for such a system is try to measure the current versus the current that passes through versus the differential resistance dV over dI for the system. Okay, and what you'll get is, so this is 0. Let me write down the actual numbers. 200, 400, 600, minus 200, minus 400, 600. So what you'll see is something like this. So what it tells us is that under sufficiently large currents, so if you apply more and more bias, you'll increase the tunneling probability. So the resistance of the tunneling junction will decrease. But below a certain threshold value, simply the energy will not be high enough for electrons to pass through this tunneling junction. Now, but this is not what I really want to see. I would like to see how my tunneling junction will respond to the individual charging. So there's one addition that you can make to this system. So you set up a microwave around this tunneling junction. And the idea is that you tune the frequency of the microwave in such a way that electrons will be constantly tunneling back and forth. And when I tune the current or the voltage that I apply, I'll be in resonance or off resonance with the electrons going back and forth, which will give me some oscillations in the spectrum. And when I draw that, this is sort of what I get. Okay, so this is with microwave on. This is with microwave off. And these oscillations called single electron tunneling oscillations. Yes. So you're really driving electrons back and forth. You're forcing them to oscillate. And then on top of that, you have another condition where you can tune with the bias. So you send extra electrons. If it is on resonance with the tunneling, it's on resonance with this charging, then more electrons pass. So you see these minima. Or you're off resonance. So the tunneling junction is already charged up, so you cannot put more electrons, then the resistance increases, so you're off resonance. So these oscillations are called single electron tunneling oscillations. And let me cite the paper. This is relatively older. Advances in Physics, 1979. Okay, so in the next lecture we'll go into more details of single electron transistors. For now I'm going to stop. Probably on Friday we'll start at 9:40 because people got really exhausted, I guess, with that schedule. We started last lecture with Shahmurat, and he was the only person for, I don't know, for 10 minutes or so. Also, I think we are ahead of our syllabus. Single electron tunneling was the topic of the 12th week. So we have superconducting devices left, and then also I'll talk about experimental measurements techniques of mesoscopic systems. So on Friday we'll finish the single electron tunneling, and the following week I think we'll talk about superconductivity and superconducting mesoscopic devices. So this will be then in the following week we'll just talk about the experimental measurement techniques for the mesoscopic systems. And with that, I think we have one more week left for probably discussing 2D materials. So I'd like to spend some time, and I'd like to review some of the experiments that we have seen that are done on 2D electron gases that are replicated in 2D materials as well. And with that, we'll finish this class. Sure.
Until which podcast lecture will come to the channel?
Well, probably we'll do single electron tunneling. Then perhaps we can include superconducting devices as well. Perhaps not. I don't know. I'll let you know. Yeah, I'll let you know. But I can guarantee that there will be single electron tunneling. Right. Efendim hanım. Yok dersteydim de. Müsaitim. Hadi ya.